Hi, I'm Wei Chu. In this video, I'm going to briefly talk about our approach to inverse problems. Many tasks in computer vision and robotics are inverse problems. The goal is to estimate the hidden parameters of interest from a set of observations. While the corresponding thought process is usually well-defined, the inverse problem is still extremely challenging. This is because a lot of information are lost during the thought process. To tackle this issue, previous work have mainly explored two different ways. One is to directly learn a mapping function from data. With the help of machine learning, in particular deep learning, they have achieved state-of-the-art results. Unfortunately, these models often ignore the fact that the thought process is none. Their system thus remain open loop, and their model cannot update the prediction based on the feedback signal. The other way is to pose the inverse problem as a structured optimization task and incorporate human knowledge into the energy function. For instance, constraints on human joint angles. To ensure that the optimization problem can be solved efficiently, there are usually multiple restrictions on the thought process and the form of the energy functions, both of which will increase the difficulty of design. Furthermore, most optimization approaches require many iterations to converge and are sensitive to initialization. Here's an example where the optimization methods get stuck at local minima due to poor initialization. Now we know the pros and cons of previous approaches. In this paper, our goal is to take the best of both worlds. Instead of restricting the update to follow the manifold, we present an approach that can bypass these constraints and arrive at the ground truth solution efficiently. The key insight is to replace the analytical update function depending on the energies with a deep neural network and learn how to update from data. This brings us several benefits. First, the learnable function G allows us to make more aggressive updates so that we can reach the ideal solution in a few iterations, as we have seen in a few slides before. Second, the data-driven formulation allows us to get rid of the handcrafted objectives and also all the restrictions on the thought process. Finally, different from classic learning-based methods, we also explicitly consider the feedback signal from the previous iteration so that we know how close we are to the ground truth and can adjust the update accordingly. Here, we show and run an example of our approach on illumination estimation. Given an initial estimation xt, which is the light direction in this context, we first leverage the thought process to render an RGB image, YT. Then we compare it with the observation image and compute the difference. As you can see, this difference image contains very rich information. The red part indicates that it's brighter than the observation, while the blue part suggests that it's darker. Based on this information, we clearly know that we should move the light source to the top a bit and then to the left a bit. We feed this difference image into the feedback network, and the network output an update on the current estimation. As you can see, the network indeed moves the light source to the top. We run the forward process and get a new rendered image. The difference becomes smaller. Our model then follows the same pipeline and update the estimation again. Note that the magnitude of the difference image is also very informative. It tells us how far are we from the ground truth. In this case, the magnitude of the difference image is smaller, so the model will learn to predict a smaller update. Through the iterative update procedure, we can produce accurate estimations that are coherent to the input observation. We train our model with intermediate supervision. In other words, We apply the loss function to each update step. At each iteration, the model learns to move aggressively towards the ground truth solution. This encourages the network to arrive at a solution within a few steps. So here's another analogy. Classic optimization approaches are like climbing the mountains up hills, while our approach is like taking gondola. We can arrive at the top of a mountain very quickly and ignore the local curvature. We apply our approach to 3 different tasks. The first one is 6-off post estimation. The goal is to estimate the rotation and translation of the object from a rendered silhouette images. We adopt PyRender as our for process rather than those differentiable renders, as it's faster and because we do not need to backpropagate through it. Comparing to the baselines, we are much faster. Our approach is also way more robust. We visualize the cumulative error plot for both rotation and translation error. We significantly outperform the baselines. Next, we show the runtime breakdown of a single optimization step. Since we do not require the for process to be differentiable, we can leverage existing highly optimized rendering machines. Hence, we are faster. As for the inverse update, we are extremely efficient because we predict the update by running a forward pass on a simple neural network. Whereas the differentiable renderers need to compute the analytical gradients and propagate them to the corresponding phases. Our approach also scales better when the meshes become more and more complicated. Thanks to the tailored, highly optimized rendering machine, our rasterization time is almost invariant to the number of phases. In contrast, soft res needs to consider soft occlusion and thus require more time. As for the inverse update, since our network predicts the update from the images, it has nothing to do with the number of phases. The speed does remain the same. The second application of our approach is illumination estimation, where the goal is to estimate the direction and position of the light source from a rendered RGB image. For the for process, we use PyRender. With the predicted update, we're able to reach the ground truth solution within a few steps. Comparing with the baselines, we are much faster. Our approach is also way more robust. In this example, the difference between our method and the neural mesh render is very obvious. We conjecture this is because the optimization methods are limited by the capability and expressive power of the differentiable renders. To be more specific, in this example, self-occlusion is a strong cue for us to identify the light direction. Neural mesh render, however, does not model it. Hence, they cannot incorporate such feature into the energy function and cannot use it for inference. Here, we show some quantitative metrics. Lower is better. Finally, we show some qualitative and quantitative results on inverse kinematics. The goal is to estimate joint estimations given joint positions. The for process is the forward kinematics function. We visualize the output of our system at different optimization steps. Through the feedback signal, we're able to recover from early incorrect estimations. As you can see, originally the elbow is incorrect, but with the feedback signal, we can rectify it. In terms of the runtime, our approach is way faster than the optimization methods. Our rotation error is also lower, suggesting that our data-driven pairs are much more powerful than the handcrafted energy functions. Comparing with a deep regressor, our model is able to leverage the feedback signal to reduce the error. In this video, we present a deep feedback inverse problem solver that leverages the feedback signal from the for process. Our approach is efficient, effective, and generic, and can be applied to a wide range of inverse problems.